Good morning or good afternoon, whatever time you chose to view this video. We are going to be talking about the stars and the Hertzsprung-Russel diagram. Okay, so the resulting diagram, this one right here, this diagram was named after two astronomers, okay? So it was Einar Hertzsprung of Denmark, and then you have Henry Norris Russell of America. So I want you to look here at this picture. This is a HR diagram or Hertzsprung-Russell diagram. So we just say HR diagram for short, right? I want you to look at this picture. Imagine plotting a random sampling of stars from our galaxy, right? The majority of these stars that are in our galaxy are going to be plotted here in this HR diagram. So you have the different components and different, different categories of stars. And we're going to actually go over this. Before you are done with this unit, you are going to be able to read an HR diagram and understand those stars and even the life cycle of stars, okay? So the majority of these stars, when plotted on the HR diagram, I want to point out it goes down from left to right in a diagonal line. So look right here, from left to right. I want everyone to really pay attention to these stars right here. All stars are important, but we're going to be talking about this right here. These are your main sequence stars. So when you hear me say main sequence stars, I want you to think about this line right here, the diagonal that goes down from the left down to the right. All of these are your main sequence stars, okay? Also, it is very important that you take notes, okay? This isn't just listening to me talk or rushing through the video. You really need to take notes with this unit because it's a lot of detail that goes into this unit. So for most space objects, we use light years, okay, to describe their distance. And I put this right here. We're going to talk about light years again later when we talk more about the origins of the universe. But I really wanted to make sure that we understood light years. If you ever see this term or you see any type of phrase talking about light years. So a light year is the distance light travels in one Earth year, okay? So one light year is about 6 trillion miles, okay? That's 6 trillion miles. And so I actually put this right here so you can see it in standard form. This is 6 with 12 zeros behind it. 6 trillion miles. That is how long one light year is, okay? So look here, how many light years away? I want you to look at this picture. Earth is approximately 8.3 light minutes from the sun. And what that means is the light from the sun, it literally takes 8.3 minutes for that light from the sun to reach Earth. And if you all remember from last week, I was talking about the distance of the sun. The sun is almost 93 billion miles away from Earth. So if it's 93 billion miles away and it only takes 8.3 minutes for the sunlight to hit Earth, that's pretty fast, right? Okay, so these are light years, a few different examples of light years. We have 26,000 light years away from the center of our galaxy, the Milky Way. So that's Earth is approximately 26,000 light years. So all of these are just pretty quick facts for you to kind of understand light years, but don't worry, we'll get back into that. But most importantly, just understand that one light year is about 6 trillion miles, okay? So let's talk about stars. A star is a luminous ball of gas, mostly hydrogen and helium, held together by its own gravity. Okay, and why is it held together by its own gravity? Well, you have what's called nuclear fusion reactions in its core, And this supports the star against gravity and produce photons and heat, as well as small amounts of heavier elements. The sun is our closest star, right? It is the closest star to Earth. And this is the sun. And I want you to look at this picture because when you look in the sky, you don't see the sun like this. When we look in the sky, we see this pretty little bright, you know, ball, maybe, if you want to call it that. But we see this beautiful light shining bright in the sky, right? But this is your sun when you're using like a Hubble telescope or any type of telescope from NASA. Scientists use different types of telescopes so that they can look at components in the universe. This is the sun right here, okay? So I want you to remember the picture of that sun when we talk further here. So really quickly, I just want to kind of go into life cycle of a star. Okay, now remember the sun is a star. It's the closest star to Earth. But once upon a time, it was a nebulae or a nebula. All right, an interstellar cloud of gas, mostly helium and hydrogen and other iodine gases, and dust in outer space. So if you can look at the backdrop of this picture, or I even put one right here, you can see a little dust cloud right there in outer space. These are nebulae, okay, nebulas. So these are going to be visible in the night sky either as indistinct bright patches of light or as a dark silhouette against other luminous matter. Luminous meaning bright, right? You're going to hear luminosity, luminous a lot. So we should be taking notes here. Okay, so a star's life cycle is determined by its mass. All right, the larger its mass, the shorter its life cycle is going to be, right? Because it's going to use up more, right? The smaller stars last longer. The larger stars are not going to last as long. So right here's a picture that kind of give you a really good visual of the life cycle of a star. They start off here as a nebula. So a star's mass is determined by the amount of matter that is available in its nebula, the giant cloud of gas and dust from which it was born. So over time, the hydrogen gas in the nebula is pulled together by gravity and it begins to spin. As the gas spins faster, it heats up and becomes as a protostar. And if you look here, you'll see the different stars they're taking place, and you have different names to these stars, right? So eventually the temperature reaches 15 million degrees, and nuclear fusion, that's that compacting in the core of that star or nebulae. So you have this nuclear fusion occurs in the cloud's core. The cloud begins to glow brightly, contracts a little, and becomes stable. It is now a main sequence star and will remain in this stage, shining for millions to billions of years to come. This is the stage our sun is at right now. Okay, so remember, our star is a main sequence star, and our star would be considered one of these average stars, right? It's, and look at the colors. We're going to go into these colors, but those colors, it tells a lot about the star's temperature. It tells a lot about the star's characteristics, which we're going to go into as we pretty much connect the stars and that HR diagram. Okay, so this is very important. Apparent magnitude versus absolute magnitude. Let me see if I can move this down here. Yes, out of the way. Thank you very much. You go way over there. There we go. Okay, so apparent magnitude versus absolute magnitude. What is important here is I want you to think about the first picture of the sun that I showed you, the very first picture. That would be considered more of absolute magnitude, right? We would need to use different equipment to see absolute magnitude, right? Apparent magnitude is almost like saying, well, apparently it seems to look this way. So this is the picture I wanted to show you with apparent magnitude, because clearly when we look in the sky, apparently what we see is a star, which is the sun, shining really, really bright. Okay. However, is that the actual brightness of the star? Or is it seeming that bright because it is so close to Earth? So while apparent magnitude is a measure of the brightness of an object as seen by a particular observer, like myself or you, absolute magnitude is a measure of the true actual brightness or luminosity of an object based on the distance. And here's a really great analogy I found online. This really, really gives you an idea of that apparent and absolute magnitude. So you have car A right here and car B. They're the exact same car, exact same car. But look at A. A's headlights appear brighter because it's closer. That's like the sun in the sky. It appears brighter than all of those little bitty stars you see in that night sky, right? You would think, oh, the stars are really, really small and the sun are, bigger than the stars. But guess what? That's because of distance, okay? Because if the sun was really as far as some of those tiny little stars you see in the sky, we would barely even see that brightness, okay? We really probably wouldn't see as much. So I want you to look here. You have a truck, right? And I want you to think about a really big truck, a big delivery truck, opposed to maybe a Honda Civic or a smaller car. And think about those headlights. Naturally, the truck would have larger headlights, right? It's going to be really, really bright. Okay, naturally. This is what we're talking about when we talk about absolute magnitude. It's that natural light that comes with the truck no matter what, okay? So car A and car B are at the same distance. Now, this time we're talking about distance, okay? They're at the same distance, but A headlight appear brighter because they are intrinsically, all right? And this means naturally appearing brighter. Naturally, the headlights on a truck are going to be bigger than a Honda Civic. So absolute magnitude would be the true actual brightness of an object. And here's another example. You have an observer sees two stars. Star A appears brighter than star B because it is closer, right? It is closer. That's like with our sun. It appears brighter to us than the other stars in the sky because the sun is the closest star to Earth. So it shines brighter. It looks way bigger, but not quite. Okay, absolute magnitude is the brightness a star would have at a distance of 10 parsecs, and we'll go into that when we talk about those light years. Okay, if stars A and B were both 10 parsecs, or 32.6 light years away, I believe that's the equivalence, away from the observer, then star B would appear brighter than star A. Okay. So the Hertzsprung-Russel diagram, HR diagram, is a scatter plot of stars showing the relationship between the stars' absolute magnitudes or luminosities versus their stellar classifications or effective temperatures. Now, I put two different pictures right here because I want you to notice these pictures. You'll see different pictures of HR diagrams. Of course, I'm giving you beautiful color here, but you may see an HR diagram that looks just like this, but it's just printed black and white. So you really need to understand how to read these and how to know how to read them, okay? Let's move this again. It's in the way. Can we move it? I think that'll do. All right. So notice the colors of the temperatures. Now, when we talk about convection currents, if you all remember, we talked about convection currents. We had the warm and the cold, and warm air rises, cold air falls, and we put red with warm and blue with cold. Well, guess what? With the HR diagram, it's total opposite. So red, if you look over here, Red would be cooler temperatures, and then the temperature moves toward the left, and blue, or that purple or indigo color, is going to now be hotter temperatures. And it says it right here. You have decreasing temperatures going toward the right, okay? But then you have increasing temperatures going toward the left. So you really need to understand that. You really, really have to understand that in order to read this diagram really, really well and answer those questions on which star is coolest or which star is hottest, right? So for example, if we look at this right now, I can tell you that the white dwarfs are going to be hotter than the giants, right? Because the giants are over here on the right side of the HR diagram, whereas the white dwarfs are over here on the left side of the HR diagram. Okay, then look at the main sequence stars. You have different various temperatures, right? You have these main sequence stars. They start up here from the left top corner and they go diagonal down to the right top corner. And these are going to be where most stars will be on the HR diagram because that's where they are going to be the longest, right? Millions to billions of years. So this is pretty much going to be your HR diagram. You're going to have your temperature here on your X axis. You're going to have your luminosity here on your Y axis. And we are going to be able to plot different types of stars. All right. Also want to make sure I point out to you right here with the luminosity. Notice you have 10 and you have this negative fourth power, negative 2 powers, whatever. However, understand that when you are going below this number 1, anything below this number 1 means that the luminosity or the brightness is becoming more and more dim, okay? But as you go up the y-axis, anything above that 1, as you go up above that y-axis, your stars are going to be brighter, okay? So for example, if we were to talk about the supergiants, we would say that the supergiants are very, very bright and cool, okay? If we were to talk about the white dwarfs, we would say that the white dwarfs were very, very hot, but dim, okay? They're very dim because they're down here. So this is how we read those different stars. Now, if you look over here on this HR diagram, I want you to notice right here is your sun, our sun, right? This is the star that is closest to Earth. And notice the sun is going to be a main sequence star, okay? This is the stage our sun is in right now in the life cycle of a star. It is in the main sequence stage. So our sun is going to have a luminosity of 1, and then the temperature is going to be about 5,500. It depends on which one you look at. So it'll be something around about there. But notice it is plotted as yellow on the HR diagram. Okay. It is plotted as yellow, which indicates the temperature in Kelvin. All right. So once again, what type of star is our sun? Well, let's go and look at it. We have one right here, and there's the sun again. The sun is going to be a main sequence star. So this is going to help you with plotting those different stars. You have your near-pod activity, which is going to also help you with this HR diagram and stars. Make sure you pay attention to that. You have a lot of different assignments talking about the life cycle of stars, also galaxies and other components of the universe. All of this information is going to be very, very important for you to pass your assignment, which is going to be on everything we're talking about right now. So make sure you're taking notes. Watch this video again if you need to. Please do yourselves a favor and draw an HR diagram and note where the white dwarfs are. Where are the supergiants? Where are the giants? Where is the main sequence stars? These are very, very important, right? Understand your y-axis will always give you your luminosity or brightness or magnitude, right? And then you have also your temperatures down here, your surface temperatures. And those letters, when you see those letters, those are called spectral classes, okay? Do a great job, make yourselves proud, and we will pick up later. Have a great day. Bye-bye.